Find somewhere comfortable tonight, wherever you are, bed, couch, somewhere quiet in the dark. Just let your body soften into whatever is holding you. You don't need to follow any of this closely. You don't need to remember a single word. If you drift away somewhere in the middle and never come back, that is exactly right. That is the whole point. Tonight we're going to travel somewhere very far away, and then, slowly, all the way back to you. We're going to spend some time with the sun, not the bright, overwhelming thing you squint at, but the quiet interior of it, the ancient, patient fire at its heart, the place where the most fundamental alchemy in the universe happens in almost total silence. We'll follow the light that comes from that fire on its long, wandering journey outward, and we'll trace it all the way here, to this room, to the warmth still fading from your skin. There is something deeply restful, I find, about contemplating things that are vast and ancient and have nothing to do with the ordinary weight of a day. Whatever today held for you, whatever you are still carrying, you are allowed to set it down for a while. The sun has been burning for 4.5 billion years without your help. It will continue without your attention tonight. So just rest. Let the words come and go like something heard from the next room. We have all the time in the world. Long before anyone understood what the sun actually was, people understood that it was necessary. Every culture that has ever existed has had a relationship with it, has oriented buildings toward it, told stories about it, offered things to it, feared its absence. The oldest human question about the sun is not really a scientific question at all. It is a question that feels almost personal, almost desperate. How does it keep going? For most of human history, that question didn't need an answer. The sun simply was. It rose and it set, and it would continue to do so, and that was enough. But in the 19th century, as science began to reach into the nature of things, the question became urgent in a new way. Because once you start asking how something works, you also have to ask how long it can keep working. And when scientists in the 1800s turned that question toward the sun, they found themselves facing a deeply uncomfortable answer. The most obvious thought was that the sun burned the way a fire burns, consuming fuel, giving off light and heat. Coal was the great fuel of that era, the thing that powered the Industrial Revolution. So someone did the calculation. If the sun were made entirely of coal and burning in the ordinary way, how long would it last? The answer, given the sun's size and the rate at which it radiates energy, was a few thousand years, not nearly long enough. The Earth's rocks alone told a story far older than that. So another idea was proposed, and it was more elegant. A physicist named Lord Kelvin, along with a German scientist named Hermann von Helmholtz, working independently, suggested that the sun might be slowly contracting, falling inward under its own immense weight, converting that gravitational collapse into heat and light the way a bicycle pump warms when you compress the air inside it. This was a genuinely beautiful idea, and it was taken seriously for decades. When the calculations were done, it gave the sun a lifespan of perhaps 20 million years. Much better, but still not enough. By the late 1800s, geologists had begun to read the story in stone with increasing confidence. Certain rocks, certain layers of sediment, certain formations carved by glaciers and rivers implied an Earth that was hundreds of millions of years old, perhaps older. And Darwin's theory of evolution, published in 1859, required deep time, an almost incomprehensible span of slow, patient change to explain the diversity of life. 20 million years enough. The sun would have burned out long before the first fish crawled onto land. This was one of the great unresolved tensions of late Victorian science. The physicists said the sun could only be so old. The geologists and biologists said the Earth had to be far older. Both were using good methods and arriving at contradictory conclusions. Something was missing. Something was unknown. It was not until 1920 that the shape of the answer began to emerge, and it came from a quiet, remarkable English astrophysicist named Arthur Eddington. Eddington had already made his name by helping to confirm one of the great theories of his era, the idea that massive objects bend the path of light through careful observations during a solar eclipse. He was a meticulous, thoughtful man, not given to speculation. But in 1920, in a paper and then in a lecture, he put forward an idea that was, at the time, almost impossible to fully support. He suggested that the sun's energy came from somewhere inside the atom itself, that somehow, deep in the core, hydrogen was being transformed into helium. That 4 hydrogen nuclei, the smallest, simplest atomic nuclei in existence, were combining to make one helium nucleus, and that the helium nucleus, when you weighed it carefully, was very slightly lighter than the 4 hydrogens that went into it. That missing mass, Eddington argued, was not lost. It was released. It became energy. And because the relationship between mass and energy involved a very large number, the speed of light multiplied by itself, even a tiny amount of missing mass could produce an almost incomprehensible flood of energy. The insight rested on a relationship between mass and energy that had been worked out by Albert Einstein just 15 years earlier. Eddington was, in essence, applying a brand new equation to the oldest question in astronomy. He was right. He was almost certainly right. But he could not yet explain the mechanism. He could not say how hydrogen became helium, what steps were involved, what force made it possible. The atom was still being mapped. The interior of the nucleus was still largely unknown. Eddington held his insight patiently, like a man who has found a door but not yet the key. For nearly 2 decades, the answer waited in that state, known in outline, unknown in detail. The mystery was held quietly in the hands of science, and the sun continued to burn, as it always had, as it would for billions of years more, indifferent to whether anyone understood it or not. To understand what happens inside the sun, you have to try to imagine conditions that have no equivalent anywhere in ordinary experience. This is genuinely difficult. None of them quite stretch to what the core of the sun is actually like. But we can try, gently, to feel our way toward it. Start with density. The core of the sun is about 10 times denser than gold. Gold is one of the heaviest everyday materials most of us can imagine. Heavy enough that a gold coin surprises you when you pick it up. Heavier than it looks, heavier than it should be. Now imagine something 10 times denser than that. Something so compressed that the matter inside it has been squeezed far beyond anything that can exist as a solid or a liquid or even an ordinary gas. In the core of the sun, matter has been pressed into a state that has no name in everyday language, a kind of dense, frenzied soup in which the usual rules of matter no longer apply. In ordinary matter, in the chair you're lying in your own body, atoms hold their shape. Each atom has a nucleus at its center, surrounded by a cloud of electrons moving in their own territories, and those electron clouds keep atoms from passing through each other. That is what solidity is. In the end, electron clouds refusing to share space. In the sun's core, it is too hot for any of that. The temperature there is roughly 15 million degrees, a number so large it becomes almost meaningless without something to compare it to. The surface of the sun, which is hot enough to melt any material we know of, is only about 5,500 degrees. The core is roughly 3,000 times hotter than that. At those temperatures, atoms cannot hold themselves together. The electrons are stripped away entirely, flying free. What remains are bare atomic nuclei, tiny, dense, positively charged, hurtling through the soup at extraordinary speeds. How fast? A particle in the sun's core moves at speeds that would carry it across an entire continent in something like a heartbeat. Not across a room, across a continent. That is the kind of frenzied, relentless motion that 15 million degrees of heat produces. And above all this, above and around and pressing in from every direction, is the weight of the rest of the sun. The sun is enormous. If you could hollow it out, you could fit more than 1,000,000 Earths inside it. All of that mass is pressing inward under gravity, and the core is the place where all that weight converges. The pressure there is something like 250 billion times the pressure of Earth's atmosphere at sea level. It is a number that defeats intuition. The core is simply one of the most extreme environments in our part of the universe. Now, why do any of these conditions matter? Why does fusion require them? It comes down to electricity. Every atomic nucleus carries a positive electrical charge, and positive charges repel each other. This is one of the most fundamental rules of nature, like charges push away from each other. If you try to bring two positively charged nuclei close together, they resist. The closer you get them, the harder they push back. It is like trying to press the same poles of two magnets together. That springy, invisible resistance that grows stronger the closer you push. Under ordinary conditions, this resistance is insurmountable. Atomic nuclei simply cannot get close enough to each other to merge. They bounce apart long before they can touch. But in the sun's core, the particles are moving so fast, given so much energy by that 15 million degree temperature, that some of them can approach each other at speeds great enough to get very, very close indeed, close enough for something else to take over. Nature has, at its deepest level, a small number of fundamental forces, a small number of ways that things can push and pull on each other. The electrical repulsion between nuclei is one of them, but there is another force, one that acts only at extraordinarily close range, so close that it is effectively invisible at any distance we can experience in daily life. At the scale of atomic nuclei, when two particles get close enough, this very short-range force becomes attractive, and it is far stronger than the electrical repulsion. It can pull nuclei together and hold them fused. The problem is getting close enough for it to kick in. The electrical repulsion is like a high wall surrounding each nucleus. Most of the time, even in the sun's core, particles do not have enough energy to get over that wall. They bounce away. But occasionally, rarely. We'll come back to that. For now, hold the image of the core, dense beyond gold, hot beyond imagining, filled with bare nuclei hurtling in all directions, the weight of a star pressing inward. And somewhere in all that frenzied motion, the slow and patient work of making helium from hydrogen, one almost impossible collision at a time. The sun is, in this sense, a study in balance. The gravity pulling everything inward is matched perfectly by the pressure of all that heat pushing outward. Remove the heat, and the sun would collapse. Remove the gravity, and the whole thing would fly apart. For 4.5 billion years, these two forces have held each other in a kind of deep, ancient equilibrium, a slow, vast, unhurried balance that has given us time enough for everything. Of all the moments in the long chain of events that produces sunlight, the first is the most improbable. It is so improbable that if you watched a single proton, a single hydrogen nucleus, waiting for it to happen, you might wait for longer than the current age of the universe. And yet it happens constantly, in vast numbers, because the sun contains so many protons that even an almost impossibly rare event becomes, in aggregate, reliable. This first step is where two protons meet. Protons are the simplest atomic nuclei, just a single positively charged particle, the nucleus of the most common element in the universe. In the sun's core, they are everywhere, moving at those extraordinary speeds, constantly colliding with each other. Most of these collisions are just bounces. The two protons approach, the electrical repulsion between them pushes back, they deflect and fly away in new directions. This happens billions of times a second, for each proton with nothing to show for it. Very rarely, almost vanishingly rarely, something different happens. Two protons approach each other and get close enough that the short-range attractive force begins to pull at them. But even then, simply being close is not enough. For two protons to fuse and stay fused, one of them must change. It must transform from a proton into something slightly different, a neutron. A neutron has almost the same mass as a proton, but no electrical charge. When one proton in a pair becomes a neutron, the pair can suddenly hold together because the force that was causing them to repel each other, the electrical charge, has been halved. The resulting particle, one proton and one neutron bound together, is stable in a way that two protons cannot be. This transformation, proton becoming neutron, is governed by one of the four fundamental forces of nature. It is the force responsible for certain kinds of radioactive decay, the one that allows particles to change their identity under the right conditions. It is enormously weaker than the short-range attractive force that holds nuclei together, and it operates across a range even smaller. For a proton to transform into a neutron in the way required, everything has to be exactly right. The two protons have to be close enough, at the right energy, for the transformation to occur at precisely the moment they meet. The probability of this happening in any given collision is almost beyond small. Scientists have calculated that in the conditions of the sun's core, a single proton might wait, on average, somewhere around 10 billion years before this transformation happens to it. 10 billion years. Any individual proton in the core is, statistically, unlikely to ever undergo this change during the sun's entire lifetime. And yet the sun contains an almost incomprehensible number of protons. In that vast population, even a probability this small produces a steady, reliable trickle of successful fusions every second. Not because the process is efficient, but because the numbers involved are so large that the rare exceptions add up to something sustained and real. When the transformation does happen, when one proton quietly becomes a neutron and the pair stick together, something else is released at that same moment. A tiny, almost massless particle shoots away at very nearly the speed of light, carrying energy with it. This particle is called a neutrino, and we will spend more time with it later. For now, just note that it escapes immediately, passing through everything around it as if nothing were there at all. There is something worth sitting with in the extraordinary patience of this first step. When people imagine nuclear reactions, they often imagine something violent and fast, an explosion, a chain reaction, something that consumes itself in an instant. The sun is nothing like that. The first step in its fusion process is so slow, so reluctant, so demanding of exactly the right conditions at exactly the right moment, that it acts as a natural governor on the whole process. A regulator, a built-in brake. This is, in a very real sense, the reason the sun has lasted as long as it has. If the first step were easier, if two protons could fuse readily, the way some other reactions proceed, the sun would have burned through its fuel billions of years ago, long before the first single-celled organisms appeared in Earth's oceans, long before anything alive had a chance to exist. The difficulty of this first step is not a flaw in the sun's design. It is the gift that makes everything else possible. There is something almost meditative in that thought. The most important process in our solar system, the one that makes life on Earth possible, succeeds precisely because it fails almost every single time it tries. And that patience, stretching across billions of years, has been enough to warm every living thing that has ever existed on this planet. Once that first shy joining has happened, once two protons have found each other and one has quietly become a neutron and the pair are resting together in a new and fragile unity, the story moves faster. Not fast in any human sense, to steps that follow are far less reluctant than the first. The newly formed pair, one proton and one neutron held together, does not stay alone for long. In the dense, frenzied soup of the sun's core, another proton comes along almost immediately. Almost immediately in this context means within about a second. After waiting potentially billions of years for the first step, the second step takes about a second. The contrast is quietly astonishing. This second proton meets the pair and, because the short-range attractive force is now involved on both sides, they fuse, The result is a new kind of nucleus, 2 protons and 1 neutron, all bound together. This small nucleus is a lighter cousin of ordinary helium, which normally has 2 protons and 2 neutrons. This 3-particle version is real and stable, and it exists in nature, though it is rare. In the moment of its formation, something else is released as well, a burst of pure energy in the form of a very high-frequency ray of light. Not visible light. A gamma ray, as physicists call it. This fierce little packet of energy is born at the very moment the nucleus forms, and then it begins a journey that we will follow in the next chapter. But first, the third step. The small 3-particle helium nucleus drifts through the core, and eventually, after perhaps a million years of waiting, it meets another one just like itself. 2 of these small helium nuclei, each carrying 2 protons and 1 neutron, find each other and collide with enough energy to fuse briefly. For a fleeting moment they are joined, a single unstable nucleus of 4 protons and 2 neutrons. But this combination is too heavy, too energetic, too unstable to hold together. Almost immediately it splits, but not into what it was before. Instead, 2 protons are released, flying back into the core to begin the whole journey again. What remains behind is a stable nucleus of 2 protons and 2 neutrons. Ordinary helium, complete, settled. This is the final product of the whole chain. 4 protons went in, across all 3 steps. 1 helium nucleus came out, and 2 protons were returned to the core as change, ready to start again. Now here is the part that is worth holding very gently, because it is where something almost magical lives in the accounting. If you could weigh the 4 protons that went into this process and then weigh the helium nucleus that came out of it, you would find that the helium is slightly lighter. Not by much, by an amount so small that no ordinary scale could detect it, less than 1% of the total. But that tiny difference in mass does not simply vanish. It cannot. Mass and energy are, at the deepest level, the same thing in different forms. That missing mass becomes energy. It becomes the gamma rays released along the way. It becomes heat. It becomes, eventually, after a very long journey, the light that reaches Earth. Every photon of sunlight that has ever warmed a human face, every ray that has ever coaxed a seed to sprout, every beam that has glittered on the surface of the ocean, all of it traces back to this tiny discrepancy in weight between 4 protons and 1 helium nucleus. And there is one more thing worth noting here, something quietly beautiful about the way these particles manage to get close enough to fuse at all. The electrical barrier between 2 nuclei, that wall of repulsion, should, by the rules of ordinary physics, be too high for most particles in the sun's core to cross. The particles simply do not have enough energy to get over it, and yet fusion happens. The answer lies in something strange and wonderful about the behavior of very small things. At the scale of atomic nuclei, particles do not behave quite like tiny billiard balls. They behave more like waves, spread out, uncertain about their exact location, capable of being found in places that seem, by ordinary logic, to be forbidden. A particle approaching the barrier it should not be able to cross will, some small fraction of the time, simply appear on the other side of it as if the barrier were not quite solid. As if it had seeped through the way water finds its way through stone over a long enough time. This is not a metaphor. It is a real and well-documented feature of how the universe works at very small scales. Without it, the sun's core would not be hot enough to produce fusion at anything like the rate it does. Without this gentle wave-like seeping through barriers, the sun would be far dimmer, or would need to be far hotter, or might not sustain fusion at all. The light we live by depends in part on this quiet strangeness at the heart of matter. Particles behaving less like objects and more like suggestions of where something might be found. The whole chain, from first step to last, is a kind of slow, patient, improbable miracle. 4 protons, 1 helium nucleus, a tiny weight of missing mass turned into the warmth of a star. And somewhere in the core, right now, as you rest, it is happening, steadily, unhurriedly, as it has been happening since before the Earth existed. When a ray of energy is born in the sun's core, that fierce gamma ray released when nuclei fuse, you might imagine it streaking outward immediately, racing toward the surface and then across space to reach us. Light travels fast, after all. The distance from the sun's core to its surface is vast by human standards, but light crosses it in a couple of seconds when nothing is in the way. Nothing in the sun's core is ever out of the way. The core is so dense, so packed with particles, that a ray of light cannot travel more than a tiny fraction of a centimeter before it strikes something. A free electron, a bare nucleus, another photon. The core is so crowded that the mean free path, as physicists call it, the average distance a photon travels before being absorbed, is extraordinarily short. The photon is absorbed almost instantly, and then, a moment later, the particle that absorbed it re-emits a photon, but not necessarily in the same direction. The re-emitted photon goes off in a random direction, travels its tiny fraction of a centimeter, and is absorbed again, and so on. Imagine trying to cross a very crowded room, a room so packed with people that you cannot take a single step without being jostled, turned around, and sent in a new direction. You might take a step forward, then be pushed sideways, then stumble backward, then lurch forward again. After a great deal of effort and movement, you might find yourself only a few centimeters from where you started. Now imagine that room is not a few meters across, but hundreds of thousands of kilometers, and that the jostling happens billions of times per second, and that you have no ability to choose your direction at any point. This is the journey of a photon through the sun. Scientists have estimated that a single packet of light energy, not a specific photon, because photons are absorbed and re-emitted and are not really individual things that persist, but a packet of energy making its way through this tortuous path takes something in the range of 100,000 to 1,000,000 years to drift from the core to the surface. Different estimates give different numbers, and the true answer depends on how you define the question, but the general shape of it is clear. The journey from the core to the surface takes an almost geological span of time. While this is happening, something else is changing too. The photon that began as a fierce gamma ray, a very high energy, very short wavelength form of light, is not the same kind of photon that eventually reaches the surface. Each time a photon is absorbed and re-emitted, the energy can be redistributed. Over an enormous number of absorptions and re-emissions across regions of the sun that are progressively cooler as you move outward from the core, the energy is gradually softened, stretched. The fierce, penetrating gamma rays of the core become, over that long drift outward, softer forms of radiation. By the time the energy reaches the outer layers of the sun, it has been transformed into visible light, into infrared warmth, into the gentler spectrum of radiation that our eyes have evolved to see and our skin has learned to feel. There is something quietly moving about this. The energy that arrives on Earth as a warm afternoon, as the light falling through a window onto a sleeping face, was born in the core of the sun as something far more ferocious. It has been softened by 1,000,000 years of wandering, passed from particle to particle through the interior of a star, gradually gentled into something a living thing can receive without harm. The sun processes its own energy before offering it to us. Then comes the surface, the outer layer of the sun, the visible part, the shimmering, roiling boundary between the star and open space, is where photons finally escape. Here the density drops enough that a photon can travel without immediately being absorbed again. It reaches the surface and simply leaves. It enters the vacuum of space. And now, free at last from the sun's interior, it crosses the distance between the sun and the earth in about 8 minutes. 8 minutes. After 1,000,000 years of wandering, the last leg of the journey takes 8 minutes. That photon, or rather the energy it carries, arrives at Earth and does what sunlight does. It warms the ground, it drives the weather, it feeds the plants, it reflects off the surface of things into human eyes. Some of it falls on closed eyelids in a dark room and is felt as the faint warmth of a morning. Some of it was stored, earlier today, in the food you ate, which grew because of sunlight, which came from a core event that happened 1,000,000 years ago. The light we live by is ancient. Every ray of it carries a history far longer than human civilization, longer than our species, longer than most of the creatures that have ever lived on this planet. It has been patient in its way. It has waited and wandered and been transformed, and it has arrived. Light is not the only thing the sun sends us. There is something else, something that travels a very different path, that carries a very different kind of message, and that passes through you right now, in this moment, in your bed, in the dark, without your knowing it at all. When that very first step in the fusion chain happens, when a proton transforms into a neutron and a pair of nuclei stick together for the first time, a small, almost massless particle is released, a neutrino. It is born at the very heart of the sun's fusion process, and unlike the light, it does not wander. It does not zigzag through the solar interior, absorbed and re-emitted, passed from particle to particle over 1,000,000 years. It simply passes through everything, almost without noticing that anything is there. A neutrino crosses the entire body of the sun, hundreds of thousands of kilometers of dense, hot plasma in about 2 seconds. Then it crosses the distance between the sun and the earth in another 8 minutes. Direct, unmediated news. While the light you see from the sun was born in the core perhaps 1,000,000 years ago, the neutrinos arriving now are fresh. They are the most current dispatches from the place where the sun's energy is made. There is a beautiful strangeness in this. You are, right now, being passed through by particles that were born in an atomic event at the center of the sun 8 minutes ago. Billions of them. Every second. Through your body, through the mattress beneath you, through the floor, through the earth itself. The planet is essentially transparent to them. They stream through the solid rock of continents and ocean floors as if none of it were there. Night and day makes no difference. When the sun is on the other side of the earth, the neutrinos simply pass through the planet to reach you. Nothing stops them. Nothing slows them appreciably. For a long time, this made them almost impossible to study. If a particle passes through everything without interacting, how do you catch it? How do you even know it is there? The answer, it turned out, was to build very large detectors in very quiet places, and to wait, and to be watching with extraordinary sensitivity for the rare moment when a neutrino does interact. When, out of the billions streaming through, one of them happens to strike a particle in the detector in just the right way and leave a faint, brief trace of light. The detectors built for this purpose are among the most striking structures ever made. Deep underground, in old mines and beneath mountains, scientists have carved out enormous chambers and filled them with vast quantities of pure water or special clear fluid. The walls of these chambers are lined with thousands of sensitive light detectors, devices so delicate they can register a single particle of visible light. The whole apparatus sits in the dark, in the quiet, deep below the surface of the earth, shielded from the constant noise of cosmic rays and ordinary radioactivity, waiting for the ghost to leave a footprint. One of these detectors, built inside a mountain in central Italy, has been particularly fruitful. It is called Borexino, and it sits beneath the Gran Sasso mountain range, about 1.5 kilometers underground. For years it collected data, watching its sphere of special fluid for the faint flashes that mark a neutrino interaction. And in 2020, it achieved something that scientists had been working toward for more than 80 years. The sun's fusion process, as we have been following it, is responsible for the vast majority of the sun's energy. But there is a secondary process, a different chain of reactions that uses carbon, nitrogen, and oxygen, not as fuel but as helpers, as catalysts that facilitate the fusion of hydrogen into helium without themselves being consumed. This secondary process had been predicted theoretically in the late 1930s, and it was known to be important in larger, hotter stars. But in our own sun, its contribution was thought to be small, perhaps 1% of the total energy output, and detecting the neutrinos that would confirm it was operating at all was considered one of the great outstanding challenges in solar physics. In 2020, Berexino announced that it had done it, after years of painstaking work, purifying the detector fluid to extraordinary levels, reducing background noise to almost nothing, analyzing data with extreme care. The team had detected neutrinos from this secondary process. For the first time in history, direct evidence of something that had been theorized for 80 years had arrived in a detector beneath an Italian mountain. The sun's secondary fusion process, quiet and minor and long suspected, had finally spoken. There is something deeply human about this kind of patience, building a machine and burying it in a mountain and waiting year after year for a ghost to leave a single footprint. It is, in its way, the same patience the sun itself embodies, the willingness to wait an almost unreasonable length of time for something that is almost impossibly rare to happen, and to be ready when it does. The neutrinos are still coming. Right now, as you rest, they are passing through you. Ancient messengers, born in atomic fire, carrying news from the core of the sun, passing through the earth as if it were morning mist. They have nothing to tell you, exactly, but they are there. They have always been there, and in their quiet, unstoppable passage, they carry the proof that the sun is still working, still fusing, still burning, 8 minutes away, patient and vast and ancient, as it has been since long before there was anyone here to notice. Step back now from the scale of individual particles and individual moments. Step back far enough that the whole life of the sun comes into view, not as a series of events, but as a single, vast, unhurried arc stretching across time in both directions. The sun has been fusing hydrogen into helium for about 4.5 billion years. That is a number that language cannot really carry. 4.5 billion years ago, the Earth did not yet exist. The solar system was still forming from a vast, slowly spinning cloud of gas and dust. The sun itself was only just beginning to ignite, its core reaching the temperatures and pressures needed to start that first, reluctant step. Life on Earth, even its simplest, earliest forms, would not appear for another several 100 million years after that. And yet the sun was already burning, already patient, already doing what it does. Every second of those 4.5 billion years, the sun has been converting hydrogen into helium at a rate that is, in absolute terms, enormous. Each second, something in the range of 600 million tons of hydrogen is fused into helium, and in the process, about 4 million tons of that mass, the tiny fraction that does not survive the conversion, becomes pure energy. 4 million tons every second for 4.5 billion years. This sounds like it should run out quickly. It does not. The sun is so immense, so loaded with hydrogen, that even at this rate, it has only used up about half its original fuel. It has, by current estimates, enough hydrogen remaining in its core to continue fusing at roughly the current rate for another 5 billion years or so. 5 billion years. By any measure of time that has meaning to a living thing, the sun is not going anywhere. It is, as stars go, middle-aged, settled, still in the long, stable middle of its life. But slowly, so slowly that no human lifetime, no recorded history, no geological epoch could detect it, things are changing inside. As helium accumulates in the core, replacing the hydrogen that has been fused, the character of the core shifts. Helium is heavier than hydrogen, and it does not fuse as readily under the conditions that prevail now. It tends to settle toward the center, forming a slowly growing region that does not participate in fusion. The core of the sun, over billions of years, is gradually changing its composition, becoming richer in helium, poorer in hydrogen, subtly denser, subtly different. This slow accumulation will eventually matter. In perhaps 5 billion years, when the hydrogen in the core is largely exhausted, the sun will begin to change in ways that are dramatic by astronomical standards, though the change will unfold so slowly that no individual moment of it would seem significant. The sun will grow larger and cooler at its surface, even as the core becomes hotter and denser. It will swell to perhaps 100 times its current size, a vast, reddish, luminous sphere that would, if the Earth still existed, extend far into what is now the inner solar system. But that is very far away. For now, the sun is steady. The balance between gravity and the outward push of heat is maintained. The rate of fusion adjusts naturally and without any external intervention to keep the star in equilibrium. If the core became slightly hotter, fusion would proceed slightly faster, producing more energy, which would push the outer layers slightly outward, which would slightly reduce the pressure on the core, which would cool it slightly, which would slow the fusion, a self-correcting loop, a natural thermostat written into the physics of the star itself. It has been doing so for 4.5 billion years. There is something worth resting in here. The elements that make up your body, the carbon in every cell, the oxygen you breathe, the iron in your blood, the calcium in your bones, were not made in the sun. The sun is a hydrogen-burning star, and it makes helium, and that is mostly what it will ever make in its core. The heavier elements, the ones that life is built from, were forged in other stars. Stars that lived and died long before the sun was born. Stars that burned through their hydrogen and then fused helium into heavier things and heavier still until some of them reached the end of what fusion could give them and collapsed and scattered their contents across space in vast, slow clouds. Those clouds drifted and gathered over millions of years and eventually, drawn together by gravity, seeded by the pressure of some nearby stellar event, they began to collapse into a new star, our star, and around it the leftover material, rich in the heavy elements scattered by those earlier stellar lives, gathered into planets, into the ground and the sea and the air, and eventually into the bodies of living things. You are, in the most literal sense, made of material that was forged in the hearts of stars that no longer exist. The sun is your contemporary, your companion in the solar system, the engine that drives the weather and the seasons and the food supply. But the atoms in your body are older than the sun. They were processed in fires that burned and went out billions of years before the sun ignited. The sun's story is also your story in this quiet, ancient way. It is the story of matter being transformed, slowly, patiently, across time, into something new. Follow the light all the way home now, all the way from that first, almost impossibly rare moment in the sun's core. 2 protons, 1 transformation, 1 neutron, 1 fragile new bond, through the million-year drift toward the surface, through the 8-minute crossing of open space, through the atmosphere, through the window, to here. You. The light that has shaped your life, that has told your body when to wake and when to grow still, has been making this journey for longer than you can really hold in your mind. And yet here it is, woven into the rhythms of every living thing that has ever existed on this planet. Life on Earth emerged under the sun, not just in the sense that it needed warmth to survive, but in a more intimate sense. Life learned to use the sun's rhythm as its clock. The alternation of light and dark, day and night, became the pulse that everything living synchronized to. Plants grew toward the light and closed in the dark. Animals became active in the day or the night, and their bodies learned to tell the difference. Over hundreds of millions of years, this synchronization became so deep, so fundamental, that it is now written into the biology of almost every living thing on Earth, including you. Inside your body, right now, there is a system of timekeeping that has been shaped by the sun's light across the entire span of your species' evolution. and the evolution of your ancestors before that. This internal clock, the one that makes you feel alert in the morning and drowsy at night, the one that governs the rise and fall of hormones, the one that tells your body when to repair itself and when to rest, is set every day by light, by the specific quality of morning light falling on your eyes, by the fading of the afternoon, by the deepening of evening. The light that sets this clock came from the sun. It was made, ultimately, by the fusion of hydrogen into helium in the core, that tiny difference in weight between 4 protons and 1 helium nucleus, released as energy, transformed over 1,000,000 years of wandering into the visible warmth that reaches Earth. The rhythm of your sleeping and waking is, in this sense, a direct consequence of atomic events in the core of a star. The sun has been setting your clock since long before you were born, since long before any human being existed. There is something very still and very large in that thought, if you let it rest with you. The warmth you feel after a day spent outdoors, that pleasant heaviness, that sense of having been held by something vast and gentle, is, in the most literal sense, the product of nuclear events that began before any human walked the earth, arriving at last as something as simple as the feeling of being warm. The energy in that warmth was, 1,000,000 years ago, a fierce gamma ray in the core of the sun. It was softened and transformed across that enormous journey, passed from particle to particle, stretched and gentled until it became something a living body could receive. You received it. And now, in the dark, some of it is still with you, stored in the warmth of your body, slowly fading into the night. Hold, for a moment, the whole arc of it, the protons in the sun's core, moving at speeds beyond imagining, almost never finding the right conditions to fuse, and yet, across the vast numbers involved, finding them reliably, steadily, for billions of years. The tiny paired nucleus forming in the dark of the core. The burst of energy released. The 1,000,000-year wandering toward the surface, that slow, jostling drift through the densest material in the solar system, the energy softening as it goes, the moment of escape at the surface, the sudden freedom of open space. The 8-minute crossing, silent and fast, from the sun to this planet, the light falling on the ground, on the leaves, on the surface of the sea, on your face earlier today or yesterday or some other day you have half forgotten. And here you are now, in the dark, the day already distant, your body beginning to let go of the things it has been holding. The sun does not need you to understand it to go on burning. It has been burning through the rise and fall of every civilization, through the slow unfolding of every species that has ever lived, through the long, patient accumulation of deep time. It will continue for 5 billion years more, steady and unhurried, fusing hydrogen into helium in the dark of its own core, sending its light outward in all directions into the silence of space. Some of that light will fall on this planet. Some of it will reach you tomorrow morning, gentle and ordinary as it always has. For now, the sun is on the other side of the world, and the dark is yours. The neutrinos are still passing through you, billions every second, carrying their quiet news from the core. The warmth of the day is still in your skin, fading slowly. The rhythms the sun has shaped in you over a lifetime, over a lineage stretching back across millions of years, are drawing you now toward rest. Let them. The light will return. It always has. It has been returning to this planet every morning for 4.5 billion years, and it will keep returning long after any of this matters. You don't need to hold any of it. The sun will hold its own fire. The atoms will do their patient work. The universe will continue its vast, unhurried business without requiring anything from you tonight. All that is asked of you now is the simplest thing: to rest, to let the heaviness of your body become the weight of sleep, to drift the way a photon drifts through the solar interior, slowly, without direction, absorbed and released, moving without urgency towards something softer. Somewhere behind you, the day is already very far away. Let it stay there. The sun is patient. The dark is kind. Sleep well.